In this video, we're going to introduce acids, bases, and neutralization reactions. And when we mix acids and bases together, the type of reaction that occurs is a neutralization. So that's where this title comes from. In a previous video, I had mentioned that strong acids and bases will completely ionize, completely dissociate in aqueous solution compared to weak acids and bases, which will only ionize or dissociate a small amount by comparison, typically maybe 1 to 5%, to give you an idea. Whereas the strong acids and bases, they will ionize or dissociate 100%. So when we define acids and bases, we can define them different ways. So the first way is this classification called the Arrhenius system. So we have Arrhenius acids and Arrhenius bases. These specify that when we add these compounds to water, they will increase H plus or hydrogen without any electrons. So just H plus, which we sometimes refer to as just a proton. So again, Arrhenius acids dissolved in water will increase the concentration. So we can think of the concentration of H plus going up. Then we have Arrhenius bases, and these will increase specifically hydroxide. So we have hydroxide increasing here. Again, these compounds have to be dissolved in water for this phenomena to be observed. So that's the first classification system of both acids and bases. Then we have our second system here, which I'll put a marking next to. We have Bronsted-Lowry acids. And those protons that we referenced here would be donated by these species. So HCl, for example, hydrochloric acid, as its name implies, this would be a Bronsted-Lowry acid, and it would donate its proton. So it would add it to the water. And in effect, we're also going to increase H plus ion concentration. But as long as a proton is donated in solution, that fits the classification for a Bronsted-Lowry acid. Down here, the Bronsted-Lowry bases, these are going to be classified as proton acceptors. So they will grab an H plus from solution and they will accept it. There's some other terminologies mentioned here. A monoprotic acid, this will only release or yield one proton, one H plus per molecule. So HCl is a good example of that as well. And then we have diprotic acid. So these are going to give us two H pluses per molecule. And sulfuric acid, the molecular formula H2SO4 is a good example of that. Collectively, these are both HCl and H2SO4 strong acids. So we're going to memorize the strong acids and then the strong bases here. And then we know that every other compound that we call an acid or base would be a weak acid or base. So here's a list of the strong acids and bases that we need to memorize. There are 7 strong acids over here. So by name, we have HCl, hydrochloric, HBr, hydrobromic, HI, hydroiodic. Then we have chloric here, which is HClO3. When we add an extra oxygen, we get perchloric, so HClO4. And then there's nitric, HNO3, and our only diprotic strong acid, H2SO4, sulfuric. So again, I would memorize these 7 strong acids and then know that anytime we mention another acid, it's going to be a weak acid. The strong bases over here, there's, a larger list here. So they're not all listed, but any group 1 metal hydroxide, so anybody in group 1, most of them are listed here: lithium hydroxide, sodium hydroxide, potassium, rubidium, and cesium hydroxide. All of these are group 1A metal hydroxides, and they are strong bases. And then most of the group two heavy metals here, metal hydroxides, calcium, strontium, and barium, these are also strong bases. The only one that we tend to avoid as classifying, as there's some dispute, is magnesium hydroxide here, which we will leave off of this list. But the remainder of the group 1 and 2 metal hydroxides, we can classify those as strong bases. So again, anybody that's on this strong list will ionize, will dissociate 100%. And then everyone else that's not on this list, we're going to say is a weak acid or base, and they only ionize a small portion. So again, these are strong electrolytes, any of these strong acids or bases. And then the weak acids or bases, we will call these weak electrolytes. So let's see here in sample exercise 5 if we can label these properly. So we have both acids and bases and then ionic compounds mixed together here. So this first here, this is calcium chloride, CaCl2. This is an ionic compound, and this is going to be a strong electrolyte. As a result, right? So all ionic compounds that are soluble in water, we tend to call strong electrolytes because they're going to ionize in water 100%. Then we have ethanol here. So this is a molecular compound, so C2H6O, all nonmetals bonded together in a molecular form. This is going to be a non-electrolyte. So non-electrolyte. Then we have third on the list here, potassium hydroxide. We just saw listed above, this is a group 1 metal hydroxide. So this is a strong base and would therefore be a strong electrolyte. The next column here, we see nitric acid, and that is on our list of strong acids. So that will be a strong electrolyte. It will ionize 100%. And then we see this compound here. It's a molecular compound. It's titled as an acid. It's called formic acid, so HCOOH, but it's not on our list. So we know that it's going to be some type of electrolyte, but it's not a strong acid, so we're going to call it a weak electrolyte. And then our last compound here, acetone, which has the chemical formula shown here. We know that it's not an acid or base by name, and we know that it's specifically a molecular compound by all nonmetals being bonded together. So we're going to classify this as a non-electrolyte. And we'll continue with our discussion here of acid-base reactions in the next video.